Welcome back to our nomenclature lecture. This is part two of our lecture. You hopefully should have finished part one, and this is part two, the rest of naming. What's in a name? Why don't we go find out? Off to the lecture now. Bye bye. Okay, welcome back here to part two of chapter six in our nomenclature. So, picking up where we left off again last time, we talked about ionic compounds, really. And remember, ionic compounds pretty much are going to have a metal and a non-metal. And the metal will transfer that electron over to the non-metal, and that will create a cation, which is positively charged, and an anion, which is negatively charged. And as we talked about, there's no sharing of electrons here. It's that electrostatic attraction that's holding these things together. The positive negative attraction. We talked about type 1 compounds. And remember that whenever a metal is involved, it is always the one that you want to look at. And a type 1, the metal has a fixed positive charge. And what that means is that's usually from the periodic table our group 1, our group 2, our group 3, which is aluminum, our zinc, cadmium, our silver. So if you've got any of those metals there with a non-metal, as we talked about, you're going to just use the whole name of the metal. The non-metal, again, here going to get the last part dropped of its name and IDE for the replacement. So again, that is something like sodium chloride, as we talked about. Sodium being group 1, which has a positive 1 charge, always fixed. We would just roll to sodium chloride. We also talked about type 2 compounds. Type 2 compounds also metal and non-metal, but the metal here going to have a variable positive charge. And again here, that's going to be our transition metals. And as we talked about, also just to the right. Once again, underneath that staircase, where we have things, again, like lead and tin and that general area of the periodic table. Although, again, they're not technically transition metals, they do have variable charges. They are pretty much named the same way as type 2. The deal on that one is because they could have a variable charge, we still use the whole name of the metal. We do use a Roman numeral here. And remember that the Roman numeral is not how many metals you have, but it is the actual positive charge that you have on one of the still going to get the IDE treatment. Remember that always in an ionic compound, as we talked about as well, both in the name and the formula, it's always the cation first, positive guy, followed by anion, negative guy second. We then talked about polyatomic ions. And remember that polyatomic ions are groups of nonmetals which frankly are sharing electrons but actually have an overall charge, so they're considered ions as well. And what we really talked about it is a couple of things. Most of them will end in ate or ite. And remember that the polyatomic ions, you can kind of group together the ones that are related to each other, and the one with the most oxygens in that group and in 8. The one with the least will end in ite. Remember, there's also some that are groups of 4 that are related to each other. And in the groups of 4, we put per in front or hypo in front if it's the least number of oxygens. Per would go in the front of somebody that has the most oxygens, like ClO4 minus is perchlorate versus ClO minus, which is hypochlorite, ITE. So again, we add sort of that per in a group of 4 that are related to the one that has the most oxygen. and we add hypo to the front of the one that has the least number of oxygens in a group of 4. As we talked about as well, probably 98% of the time, 99% of the time, you will find the polyatomic ions basically hooked up with a metal, which means that we typically will then fall back to our type 1 or type 2 rules. Again, the metal taking the precedent, our priority in terms of how you would name it. If it is a type 1 metal that's with a polyatomic ion, then we would not use a Roman numeral. If it's a type 2 metal with a polyatomic ion, then we would use a Roman numeral. A couple other considerations we talked about, there are polyatomic ions that end in IDE, like hydroxide, cyanide. We also, if we put an H plus in front of a polyatomic ion, we add hydrogen in front of the name. In addition, if we have more than one polyatomic ion in a formula, we do need to use parentheses like CuOH2. So again, more than one, you do need those parentheses. All right. So the other important thing when we talk about ionic compounds is the idea that when you do put anytime a positive ion, which is a cation, together with a negative ion, which is an anion, we always need to make sure that the overall charge when we put them together equals 0. And we want to do that in the simplest way possible to get to 0. So that's the important thing to remember with that. And lastly, if we were to write the formulas for just ions by themselves, again, not attached to anybody else, cations or anions, we do need to make sure that we include the charges in the actual formula. But remember that when we put the metal and non-metal together in an ionic compound formula, we do not have charges. Okay. So why don't you take a moment, and we have a nice little table here. Why don't you write the correct formulas for each of these guys? And except for, why don't you start with just that, actually? Except for, if I can find my thing here, there it is. Except for this row, why don't you also, for the combinations that you make for these rows here, and again, not this row for now, why don't you also figure out what the name should be here? So take a moment. I would probably pause here the video. Take a moment and write the proper formulas by putting these ions together. Like the example here, the K with the Br, the K with the O, the K with the NO3, then the magnesium with the Br, the magnesium with the O, the magnesium with the phosphate, and so forth. So take a moment, probably more than a moment, fill in all the boxes there with the proper formulas to balance everybody out to 0, and then also give the names for everybody that's there. So hopefully you pause the video, you have this table pretty much filled out. You also have the names. Again, if you didn't, you might want to pause it again and do it before we go through it here to make sure you are doing these things correctly. All right, so I'm going to start with potassium. I'm going to work my way across this row. So potassium has +1. Obviously here, this is -1. So when we put them together here in the first box, like they demonstrated for us, we just need one of each and we will have 0 charge. Coming to our next guy, which is a -2 charge with our +1 charge. Again, to equal 0, we would need not 1, but 2 of the potassiums and only 1 of the oxygens there. Coming to our next one here, this is a polyatomic ion, has basically an overall charge of -1 that we're putting together here with a +1, which means we just need 1 of each, which will give us KNO3. Phosphate, which has a -3 charge. And we're going to put it together here with our +1. So basically putting together +1 and -3. So we will need 3 of the potassiums. So K3PO4. Lastly, here we got +1 and -2 happening. So again, we would actually need more of the potassium. So K2CO3. All right, so filling in our next row here, get rid of some of the scribble here as we can see. And then the next row here, we are putting in +2 and -1. So we need more of the Br. So we need MgBr2 +2 and -2, which means we just need one of each, MgO. +2 and -1, we need 2 of the nitrate in this case. So that's an Mg. Once again, we need parentheses, NO3 2. Here we have -3 and -2. Common number there is 6. So we actually need 3 of the magnesium to get to 6. We need parentheses there for our phosphate. And we need 2 of them to get to 6. And last we have +2 and -2. So that's just going to be a 1 of each situation. So hopefully you're doing good so far and we're agreeing on our answers. Let's go to the next one. We've got +3 and -1. Going to give us an AlBr3. +3 -2. That's a 6 combination. So we need 2 of these to get to 6. And we need 3 of those to get to 6. 3 and 1. We will need some parentheses here. We will need 3 of those NO3 minuses. 3 and 3 means we just need 1 of each. 3 and 2 means we need 6 for our common number. So we'll need 2 of the aluminums there. And we will need, once again, parentheses here and a 3. Going down to our next row here, we have a +2 and a -1. So again, we need to get 2 of the Brs in this case. +2 -2, 1 of each will do it. +2 -1, we need parentheses. And 2 of the nitrates. +2 and -3, so 3 and 2 is 6 there. +2 -2, going to give us ZnCO3. Lastly, here on this particular one, we're going to take H plus and Br, which is HBr. H plus and O2 minus, going to give us H2O. H plus and NO3 minus, which would give us HNO3. H plus and 3 minus, going to give us 3 H's we need to balance out that -3 charge. And lastly, H plus and -2, we will need 2 of those there to balance it out. Now, hopefully you filled in your table correctly. Again, the goal here, they're all ions, cations and anions coming together to make 0 in terms of the overall charge. All right, so what should the names be? Here we go. That there. All right. So let's do some naming here. First off, that is potassium that we have here. So the K plus is potassium. The Mg2 plus is magnesium. The Al3 plus is the aluminum ion. The Zn2 plus is the zinc. And again, we will save this for maybe another time here. So we didn't talk about some of this naming part yet. All right, on top here are negative guys. These are the guys get the IDE, that is bromide. That is oxide. That is nitrate. That is phosphate. And that is our friend carbonate. All right, so what are all these names? I'm going to go through them and hopefully you agree with me. So we know automatically this is type 1, which means we don't need a Roman numeral, so we could roll through the name. That should be potassium bromide. That should be potassium oxide. That should be potassium nitrate. That should be potassium phosphate. That should be potassium carbonate. Again, no Roman numeral needed. So whole name of the metal and basically whole name of the anion as well. Either the IDE or the polyatomic ion's whole name. All right, through the next ones here. It's again Mg2 plus type 1 metal, which means magnesium. So we got magnesium bromide, magnesium oxide, magnesium nitrate, magnesium phosphate, and magnesium carbonate. Once again, no Roman numeral needed. For the polyatomic ions, whole name of the polyatomic ions. For the elements, IDE at the end of it. Coming to our next one, which is aluminum, also type 1, no Roman numeral needed. We are going to go with aluminum bromide, aluminum oxide, aluminum nitrate, aluminum phosphate, aluminum carbonate. Coming to the next one, that is zinc. Is a transition metal, but it's one of those ones that we talked about which has a fixed positive charge, which means it also is still a type 1 compound. So that means no Roman numeral needed. We could roll through like we did the rest of them. That would be zinc bromide, zinc oxide, zinc nitrate, zinc phosphate, zinc carbonate. So hopefully you had those names as well. Again, the last row there, we have some acids happening, which we haven't just talked about yet. We'll get to that next. So we'll save those names for a bit. All right, let's take a look at another table here. And why don't you again do the same thing on this one. Get us the proper formulas for each of those boxes when we put them together. And why don't you take the time there to also give the proper name. Once again, I would recommend you pause the video here and make sure that you get all that information down before you continue on and see what the answers are. Remember, it's better to check your answers than just to copy what I say, right? So take a moment to do that and we'll pick back up in just a sec. Okay, let's take a look and see how you did. So again, hopefully you're replaying this with your table filled in and names happening. So same thing, we got cations, which are positively charged, anions, which are negatively charged. Once again, the goal here is to get to 0. So let's do it. We got +1 here and -2. So we actually need 2 of the first one. Since that is a polyatomic ion, we will need parentheses and a 2 on the bottom, SO4. +1 and -1 means we just need 1 of each of those. No parentheses actually needed. The one they filled in, that's +1 and -3. So we need 3 of those. So once again, we see the parentheses and 3. -1 and +1, once again, do not need parentheses. Just need 1 of each of them. Squeeze into that box, and I should not have a charge there. So sorry. Overwrote there. And lastly here, we have +1 and -2. So once again, we will need 2 of our +1. So we'll put parentheses with a 2, and we will put CrO4 there. So that's a 2. There we go. Rolling to our next row here, +2, -2. So that's 1 of each. +2, -1. We will do 2 of our -1s. plus 2 minus 3, common number there is going to be 6. So to get the calcium to 6, we will need 3 of them to get our arsenate. To 6, we will need 2. Plus 2 and minus 1, we will need 1 of the calcium. We will need parentheses, and we will need 2 of these guys. They're run into the next box. Plus 2 minus 2, we'll just need 1 of each. Coming to our next one, plus 3 minus 2, so common number 6. So that's why they needed 2 of the 3s and 3 of the 2s. Plus 3 minus 1 means I do need parentheses and a 3. Plus 3 minus 3 means I just need 1 of each. Again, no parentheses actually needed there as it is 1 of each. Plus 3 minus 1, so I will need 3 of the minus 1s there. So that also will require parentheses. Plus 3 minus 2, common number there is 6. So to get the iron to 6, I need 2. To get the chromate there to 6, I will need 3. So that's CrO4, and that's it, 3. Silver plus 1 minus 2, I will actually need 2 of the silver in this case. Plus 1 minus 1, 1 of each will do. And I actually don't need the parentheses, so I got all parenthesis happy there. AgOH should work. Here, plus 1 minus 3, I will need 3 of the silver. Plus 1 minus 1, I will just need 1 of each. No parentheses actually needed here. Plus 1 minus 2, I will need 2 of the silvers in this case, CrO4. Lastly here, plus 2 and minus 2, 1 of each will do me here. Plus 2 minus 1, I will need, actually go below here, 2 of the hydroxide. Plus 2 and minus 3, common number 6, which means I will need 3 of those to get to 6. I will need parentheses. And I will need 2 of those to get to 6. Next one, plus 2 minus 1. I will need parentheses here for my acetate. And I will need a 2. And lastly here, plus 2 minus 2. So we'll just go down here. Cu, 1 of each of those should do me. And we should be good. All right, so let's talk about actually naming here. Hopefully you did good on that boxes with the formulas. Coming over here, this row has NH4 plus, which is the ammonium ion. Ca2 plus is calcium ion. Fe3 plus, that is a type 2 guy, which means that is iron Roman numeral 3. Do you need a Roman numeral with that guy? That is silver, which is a transition metal, but one of those ones that have a fixed charge, which means I do not need a Roman numeral. And lastly, copper, which is a transition metal, means that I do need a Roman numeral. The right letter would help as well. So let's do it Cu2 plus here. So that's going to be copper Roman numeral 2, as that again is a type 2 compound, our metal. Coming up on top here, we got sulfate. We have hydroxide. We have arsenate. This is acetate. And that is chromate. All right, now we got the bases of all of our names going on. Let us roll through these like we did last time. Here we go, highlighting as we go along which the names are. So hopefully you have these down. All right, so starting here, that is a polyatomic ion, which means don't have to worry about Roman numerals, just use the whole name. So that's going to be ammonium sulfate, ammonium hydroxide, ammonium arsenate, ammonium acetate, ammonium chromate. I mean, here, that's calcium, which is a type 1 metal, no Roman numeral needed. That means that this would be calcium sulfate, calcium hydroxide, calcium arsenate, calcium acetate, calcium chromate. I mean, here, as we have the Roman numeral there, it is a type 2, so we do need the Roman numeral. This would be iron, Roman numeral 3, sulfate, iron, Roman numeral 3, hydroxide, iron, Roman numeral 3, arsenate, iron, Roman numeral 3, acetate, iron, Roman numeral 3, chromate. Silver, type 1, exception of a transition metal. That means that this would be called silver sulfate, no Roman numeral. Silver hydroxide, silver arsenate, silver acetate, silver chromate. Lastly here, copper with a Roman numeral 2, because it is a type 2 compound. Here we go. Copper, Roman numeral 2, sulfate. Copper, Roman numeral 2, hydroxide. Copper, Roman numeral 2, arsenate. Copper, Roman numeral 2, acetate. And copper, Roman numeral 2, chromate. So hopefully you had those names down correctly as we went through them. All right, so that was a good, hopefully, review for you of what we talked about in the first video, how to properly put everybody together to equal 0, how to also name these guys with or without Roman numerals, and polyatomic ions. The next thing we're going to talk about then is how we go about naming acids. And acids are substances that have the ability to produce H+, which is the hydrogen ion in solution, are sometimes referred to as the hydronium ion, which is something that's similar. It actually has a form of H3O+. In acid-base chemistry, as you will learn when you talk about that, H+ and H3O+ essentially are the same thing. So H3O+ is the hydronium ion, which means the acid part of the solution, or sometimes people just refer to it as H+. An acid is something that has the ability to basically produce free-floating H+ or H3O+ in the solution, and that's what makes something an acid. So how do we name acids? Well, frankly, we name acids by whether or not oxygen is involved. So if the answer is there is no oxygen in your acid, the acid will start with hydro, something ic acid. Now, for all acids, the cation, or the positively charged ion, is always H+. So H+ is always the positively charged ion when we are dealing with acids. So if we have something like HCl, that is basically H+ and Cl-. So no oxygen. So this would be hydrochloric acid. You had HBr. Once again, no oxygen. So that would be hydrochromic acid. This would also be H+ and Br-, basically, are the two ions that are present. Now, why am I writing this AQ next to it? AQ means aqueous. It basically means a water environment, and all acids are pretty much solutions, which are aqueous. And so that's how you know really it's an acid. So for example, as we talked about earlier, if you had HCl in the gas phase, not in the aqueous phase, you would call that hydrogen chloride gas. But if you take hydrogen chloride gas and you dissolve it in water, you create HCl that has the aqueous symbol next to it, that AQ. And that basically means it's a solution. And that would be the acid version, which would be hydrochloric acid. Same thing here. If this wasn't an acid, it wasn't aqueous, it would be called hydrogen bromide. But because it's aqueous, it implies it's an acid, and you would call it hydrobromic acid. That means that when you write formulas for acids, you should also include the aqueous symbol next to it. It is proper to do so to indicate that it is an acid. Now, if it is no, that is how you go about naming it. By the way, the missing part here is the negative charged ion. As you can see here, Cl, that's why it's hydrochloric. Here it's Br, which is why it's hydrobromic. So that kind of missing part is the negatively charged ion, is what you put there. Now, if your acid, the answer is yes, there is oxygen. Your acid will most likely contain a polyatomic ion. And as we talked about, those polyatomic ions end in one of two ways, ate or ite. So if the answer is yes, it contains oxygen and your polyatomic ion ends in ate, your acid would be something ic acid. So for example, HNO3. NO3 is nitrate, which means this acid would be nitric acid. You had H2SO4. SO4 is sulfate, which means this would be sulfuric acid. Why do I have two hydrogens there? Remember that the cation is always H plus for an acid. So this guy is H plus and NO3 minus, plus 1 and minus 1 equals 0. This is sulfate, which is SO4 2 minus, and that is H plus. So minus 2 and plus 1 means I need one more H plus to balance it out. So again, acids are really kind of like ionic compounds in that sense. You want to equal them to 0, with the H plus always being the cation. Now, if your acid does contain oxygen and your polyatomic ion ends in ITE, your acid would be something OUS acid. So if you had HNO2, NO2 is nitrite, which means this would be nitrous acid. You had H2SO3 is sulfite. That would make this sulfurous acid. So if it ends in ite, your acid will end in OUS. If your acid ends in ate, it will end in ic. So again, you could think like you ate too much, you feel icky. That's a good way to remember that maybe as well. You could see in both of these cases, if it contains oxygen, there is no hydro in the name. So do not do that. People always want to put hydro on everything. Hydro is only for acids that do not have oxygen. So why don't we try some here and see? Why don't you give the name of each of these acids? HI, HCO3, H3P. Let's do carbonic acid. Let's do chlorous acid. Let's do sulfuric acid. All right, so guys on the left, let's go proper names. Ones on the right, let's go proper formulas. See what you come up with here. Okay, so let's take a look here. So first off, I see aqueous, I see hydrogen, I see I. That means that this is basically H plus and I minus, which is why we have two of those. I do not see oxygen here, so I know that this is going to be hydroiodic acid. And again, hydro because no oxygen present. Here I have oxygen present and a polyatomic ion, which is CO3 2 minus. That's carbonate. And that's basically H plus and CO3 2 minus, which is why I have two hydrogens there in the formula. This means as carbonate, which means this is going to be carbonic acid. Here again, I see oxygen and hydrogen and aqueous, and that is phosphate, AT. That is H plus and PO4 3 minus. That is why I have three of the H pluses there to balance it out. That means that this would be phosphoric acid. All right, so hopefully you had those names there for the acids. Let's now take the formulas and see if we could work our way backwards and a good way to do this. Let's take a look. First off, I do not see hydro, which means this is a polyatomic ion, and that polyatomic ion contains oxygen. I also see ick, which means if I get rid of the ick, I know that came from an 8, which was the polyatomic ion. Now, if I just read what I wrote, that's carbonate, which means we have CO3 2 minus, which we already had on the other side, apparently. And remember that all acids have an H plus. So we're going to put these together, and we would need two of these H pluses to balance it out, which would give us H2CO3 aqueous here. That was not really the one I was going for. So when we write the one that I really meant to write, which was carbonous acid. So if we look at this here, again, no hydro. We see OUS, which means the polyatomic ion came from that, which would be carbonite instead of carbonate. And maybe we're not sure what that means, but we know carbonate is 3 and 8 is more oxygens, which means I should have one less oxygen. And we would have our H plus, and we would need obviously two of those. And we would end up with H2CO2 as our acid name. All right, so let's come back to this one here. Chlorous acid, once again, no hydro, which tells us it contains oxygen. OUS means it ends in ITE. So that is chlorite. And chlorite is ClO2 minus. And once again, our acid cations always H plus. So putting those together, we just need one of each, HClO2 in this case. Hydro tells me that it does not contain oxygen. So that's an H plus, and sulfuric means that it should be S2 minus. And then we would balance that out and make it H2S in this case. And down here. So again, the key with acids is whether or not it contains oxygen. And again, if you have the name, you can kind of, especially with the ones with the polyatomic ion, if you're not sure which one it is, you can kind of cross out the last part and put back either the 8 or the ite, and you'll be able to kind of know what polyatomic ion you should be dealing with. All right, so the last type of naming we're going to talk about here are type 3 compounds. And type 3 compounds are different. They are two nonmetals together. And here we actually do have sharing of electrons. So in this case, we have sharing of electrons. They are probably the easiest to name, but frankly, they are the one that people screw up the most on, probably because they think it can't be that easy. So we've waited a long time through our naming conversations here in these two lectures, and I kept telling you no prefixes should be used. Well, guess what? We have now come to the part where, yes, check, check, check. This is where, and really only place where, you should use prefixes. So this is the place where we do use prefixes to name these nonmetals. We use prefixes like mono is 1, di is 2, tri is 3. I think I have a table coming up here of each of these. Tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8. I'll go up. Nona is 9, so I don't write on my head in the picture, I think. And deca there is 10. Wow. So this is the place where we do use prefixes. The nice thing about this is that they're actually sharing electrons, which means there's no ions. So there's no charges to balance out. There's nothing like that. You essentially just need to use the correct prefix in the correct situation. And other than that, that's all you have to do, basically. So the way that we go about doing this is the first element in the formula is named first, and we do use the whole name of it. So what we do is we use a prefix if needed. We'll talk about that in just a second. And the whole name, first element. Then we use a prefix for the second guy, and that guy is going to be our non-metal like normal with the IDE treatment at the end of it. Now, a couple of things. We do not use mono on the first name, but it is okay to use it on the second name. So you don't use mono on the first name. You would just use the element name, but you can use it on the second name. So here's that table of prefixes and a couple of things like we talked about there. No mono on the first name, but okay on the second. So CO, for example, that is 1 carbon and 1 oxygen. They are both nonmetals, which tells you it's type 3 because they are both nonmetals. So basically 1 carbon means mono for that guy. 1 carbon means mono for that guy. We do not use mono on the first name. So this would be carbon monoxide. Now, another consideration that happens, and as you can see here in this example, is sometimes when you use a prefix, and actually here, when you use a prefix, the last vowel of the prefix and the vowel of the element name back up to each other. So we got 2 O's in this case, and we have maybe a case where we have an A and an O that happens. So in that situation, this is not really known as carbon monoxide. In a situation where we get 2 O's together, an A and an O, we do drop the prefix off, or the vowel off of the prefix. So we would get rid of that, and this would be known as it is known as carbon monoxide. So usually if you end up in this situation from your prefix, an O, and then the first letter, or from your prefix, an A, and the first letter, we typically will drop the prefixes vowel in our spelling of it. Okay, though, is usually it's okay to back up two I's to each other, but basically your O and your O or your A and your O, we do need to get rid of that extra vowel. That's what we see here. We also see it with tetroxide. So again, we have the A and the O that's backed up to each other here. So we do get rid of the A. And here we have that O like we just did there. Now, there are certain guys that are named by their common name. So if you do see H2O on anything, it is not a trick question. You should put water, move on with your life. It'll be okay. Don't put like dihydrogen monoxide, because nobody wants a refreshing glass of dihydrogen monoxide, right? Probably why they don't use that name. We would like water, right? A nice refreshing glass of water. So don't use that. NH3, which should not be confused with that polyatomic ion that we talked about, which is ammonium. Remember, this is ammonium ion. This is ammonia, no charge. So don't confuse those two. They are two different things. We'll add one to the list here, which is methane. That is the simplest organic molecule you could have. It is the gas that comes out when you light a Bunsen burner, and that is CH4. So you see CH4, you see NH3, or you see H2O. You should go by the common names, which is water, ammonia, and methane. There's a bunch more, as we saw in that first table in the very first slide of the first part of this lecture. But really, these three for our class, you should definitely go by these names. All right, so let's try some here to finish it out. So here on the left, why don't you give some names, and let me give you some names where you can write some formulas. Let's do dinitrogen pent oxide. Let's do a little carbon tetra bromide. Yeah, let's just make up some stuff. Man, I'm just kidding. Maybe I'm not. Dioxygen tri All right, so let's do names on the left there and formulas on the right. Okay, so let's take a look at these now. I personally think that these are probably the fastest ones you should be able to do. But again, sometimes people try to do all kinds of weird things they shouldn't, and maybe mess things up. So the nice thing about these is once you recognize that it is a type 3 compound, which means it has two nonmetals, you don't have to worry about balancing charges or anything like that. Pretty much just pick the right prefix and you're good to go. So let's take a look here in C. We definitely have I, which is a nonmetal, and we have O, which is a nonmetal. So that tells us it's type 3. I see 2 there, so prefix is di. I see 7, prefix is hepta. Now we're going to put it together. So di and a whole name there of the first guy. Again, the 2 I's are okay. So diiodine, and here we would drop off the A from the hepta, and we again give us the IDE for the last guy. So diiodine heptoxide. Here, that is a nonmetal carbon, a nonmetal oxygen. So again, that tells us type 3. We have 1 carbon, which is mono. We have 2 oxygens, which is di. Once again, we do not use mono on the first name, so that means we're just going to use the whole name, which is carbon and dioxide. Once again here, phosphorus is a nonmetal. Chlorine is a nonmetal. So again, telling us type 3. Once again, we have 1 phosphorus, which is mono. We have 3 chlorines, which is tri. Once again, we do not use mono on the first name, so we're just going to use the whole name, which is phosphorus and trichloride. Now, if you think those were fast, you should actually be maybe the fastest ones that you will ever do should be the guys on the right. So what do I mean by that? As soon as I see prefixes like di and penta, I know it's a type 3. And that means don't need to figure out anything other than write what it says. So di is 2 and nitrogen is N, so that's an N2. Penta is 5, oxide is oxygen, O5, right? Nothing to balance, just pretty much write what it says. I see no prefix here, but I do see one here, and that tells me that this guy, the only time we don't use a prefix on the first name is when it's mono. So that means I just have one of those, so that's a C. Tetra is 4, and bromide is Br, so boom, done. Prefix, type 3. Di is 2, oxygen is O, so that's an O2. Tri is 3, chloride is Cl, and this made up guy, perhaps we end up with something like that. So these type 3 are really the fastest ones that you could do, as long as you remember to do them again correctly. Don't do some weird things. So remember that in terms of naming, type 1, type 2, type 3, they all have really their own sort of way of naming things. So type 1 compounds, no Roman numerals, no prefixes, just the whole name of the metal, and IDE for the nonmetal at the end. Type 2, prefix, so whole name of the metal with the appropriate, no prefix, Roman numeral for type 2. So let me say that again. So Roman numeral for type 2, and that means whole name of the metal plus Roman numeral to indicate the charge on the metal, and IDE for the nonmetal. Type 3, that's my prefix. Prefix for type 3. Again, no mono on the first one, okay on the second one. But basically prefix, whole name of the first element, prefix, and IDE for the second element. So there's no mixing of any of those things. So if you find yourself Roman numering, maybe that's a word, and you are prefixing at the same time, there's a good chance you are incorrect. So there's not a lot of mix over. Remember that the only time you might find a Roman numeral and a prefix together is in the polyatomic ion situation, where the polyatomic ion itself actually has a prefix in its name. So the last type of sort of naming I just want to cover, why I got an extra slide, why not, are what are compounds that are referred to as hydrates. And hydrates are actually a lot of times solids that have crystallized with some water molecules. And they actually have kind of an interesting sort of formula, the way they're written. So for example, MgSO4.7H2O. So they typically will have a dot between two parts of the hydrate. The hydrate in the front part is what is sometimes referred to as the salt part. It's really just an ionic compound. And the second part is the hydrate part, which is basically the water part. So when we name these, we actually use prefixes, just like we were just talking about, for how many waters we have. The front part here is named like either a type 1 or type 2 compound. So that is definitely a type 1 metal, which means this would be magnesium sulfate. Now 7 is hepta, 7. And instead of water, we call it hydrate. So that would be magnesium sulfate heptahydrate. Even if you had a something like this, FeNO3, 2.3 waters. That is a type 2 metal. So we do need to figure out the charge on it. We do have 2 nitrates. It gives us a -2, which means this is +2. So this would be iron, Roman numeral 2. Again, for the charge here. Once again, we would name this like normal. So even though there's 2 of them, it would be nitrate. There are 3, which is tri, and again, hydrate. So hydrates are interesting things, and they're named a little bit differently. And they also have that little kind of dot between the salt part or ionic part and the water part. If you're going backwards in terms of you had to name like calcium, sulfate, hydrate, you would just take it kind of the salt part and the water part. So this would be a type 1 compound because that's calcium has a fixed charge of +2 as it's group 2. That is sulfate, which is our polyatomic ion. So putting that together like normal to equal 0, we would just need 1 of each. Hexa is 6. Again, hydrate is water. So here we would do a dot and 6H2O. Again, if we had something like copper 1 nitrate hexahydrate, we would do the same thing. That's definitely a type 2, so that's a copper with a +1 charge. That is nitrate with an NO3 minus. -1 +1 means CuNO3. Hexa is 6. Hydrate is water. Again, a dot 6H2O. So just want to touch upon hydrates. You sometimes come across those guys. Again, they kind of have a salt part or an ionic compound part. They have some water to sort of crystallize with them a lot of times. And that's the way we go about naming it. Well, that should conclude naming. I think now we are out of naming, and now you should be professional namers. That's a good deal. And this also should conclude chapter 6 here. So once again, thank you for watching, and have a good night or morning or afternoon whenever you're watching it. And I guess we'll see you on the next one. Have a good one. Hello, and welcome to the end of part 2 of our nomenclature lecture. Since we talked about naming in this chapter, let us finish it out with a nomenclature joke. If H2O is the formula for water, what would be the formula for ice? Is it H2O cubed?